Okay, so I was asked to provide an example of how to do a division problem using the simplified division hardware that is in Patterson's and Hennessy's Computer Architecture Risk 5 textbook. So in this case, I'm going to do 11 divided by 3, which we see right here. And I've already set up the table and placed in my initial quotient, divisor, and remainder, right? The divisor of 3 goes into the left half of the hardware, and the remainder is initialized into the right half of the hardware. And each step 1 is basically take the remainder equal to the remainder minus the divisor. Again, this is using the algorithm that's in figure 3.9 of the textbook. So what I'm going to do here is I'm going to take the divisor and subtract it from the remainder and place it into the remainder. Now this is direct binary subtraction. It may have thrown you off if you thought, well, I'm going to do like a 2's complement sort of thing and see how that works out. And that's not going to work here. So the first part of this is going to stay the same. So I'm going to have, because it's just zeros here that we're subtracting. Then the other part is I'm basically taking a 0 and subtracting a 1 from it. This is going to cause the bits to flip as we go about sort of, in a way, right? We basically have to borrow from previous columns going throughout the remainder of that number, and it's going to cause, because of how that borrowing occurs, it's going to cause later ones to actually flip, right? So, but to a 0. So that'll be a 1 there. That'll be a 0, all right? Because of the borrowing of the 2, and then we have to borrow to go to this column, so that'll be a 1 minus a 1, essentially for one column over for this one. And then it's basically we're borrowing these 2's from wherever, and that causes the bit flips to go the rest of the way across the register. So we have that in there, all right? I'll just bring these down. Or at least that's how I understand that step to be, okay, with this hardware and that algorithm. So after all this is done, it says basically we have to do step 2b in the algorithm, right? Basically says restore the original value by adding the divisor register to the remainder and placing the sum in the remainder register. So basically we're going to add it back in this case. So again, if we see this here, we'll see that we have the 1 1, we're going to be adding that here. So this part stays the same, all right? But here, as we start to add the 3 there, right, or the 1 1, basically, it's not really 3, it's 32, right? We start adding the 32 back in, it's going to cause carries the cascade back across. So the 1 and the 1 is a 0, carry the 1, right? So, I'm sorry, the 1 and the 1 is going to be the 0, yeah, which is fine. And then that's going to give us a 1 that we have to carry plus the 1 here. So the 1 and the 1 is a 0 again. Carry, we end up with a 1 again, right? The 1 and the 1 is a 0. Carry the 1, and then we basically flip all the bits back to how it was before. This is how the algorithm works. You may think, well, this doesn't seem to be very efficient, all right? Oh, on here, the next thing we have to do is we shift the quotient register to the left. So we're going to shift this left 1 bit, right, from here. This all shifts over, and we set the least significant bit here to a 0. So basically, we're switching this one. It doesn't do anything, all right? We basically moved it over, and it's a 0, so it's effectively the same thing. But we follow the algorithm, all right? And then this we just rewrite, and then step 3 is always going to be to shift the divisor register over 1 bit. So bring that over, and then we're going to shift that over 1 bit, right? And that's one whole step of this, right? And then again, we're going to add this divisor to this remainder again, right? So what that's going to do is it kind of sets us up here, right? To having the same part here, all right? So it's 1, 1, 0, right? and then this one here with that one here makes it 0. Alright, yeah, it makes it 0. That one subtracted from the 1 is a 0. And then notice again we have the 0 and the 1, so we're subtracting that 1 from that 0. So that basically causes all these other bits to flip again. So, you know, in this case we're basically taking the the 17, right? Is that right? Not 17. The yeah, the 6 to the 20, and we're subtracting it from the 11, right? So, nope, that's not right. 0, 1, 2, 3, 4. 2 to the 4th, 16. 2 to the third, 8. So the 24 minus the 11. Okay, so we end up with negative 13 there. All right, so so we got that. So now we just bring these other numbers down here, and again, this is less than a 0 remainder, so we use step 2b here, and then we're going to just add this back in here, and again we'll end up back kind of where we were before, all right, by adding this into this, all right, and right. So again, you know, that part's going to stay the same just like it was before. That 0 is going to stay the same like it was before. It's that 1 here and that 0 there that gives us a 1, and that 1 gives us a 0, and we have carries all the way back across. And then that quotient again gets shifted 1 bit, right, to the right. I'm sorry, to the left, and then it gets, you know, gets set to 0, which again makes it not do anything. And then we have to, in step 3, shift our divisor right 1 bit. So we end up with that. So now, again, we repeat the same thing. We set our remainder equal to our remainder minus our divisor, right? And I'm going to try to do my best not to let this go out of frame here, right? So again, when we do this, we'll end up and we have the 1, 1, 0, 0. So again, these two will come down as 1s. All right, this 1 subtracted from the 0. We end up having to borrow from here, which actually does have a value to start with. So that'll give us a 1 because that'll be the 2. The 2 we'll end up borrowing from here, from this column, to get our 2 minus our 1. And since we borrowed from here and it's a negative, we have to keep going back and borrowing bits. All right, so we basically end up with a 1, and then all the remaining bits get flipped for us, right? So in this case, we basically end up with negative 1, right? Because in this case, this was 12 minus the 11, so a negative 1, so it's essentially flipping all the bits there. All right, again, we have our quotient here. We got to move it over, and again, we're going to end up with setting it to 0, right? So we shift the quotient left 1 bit, set the least significant bit to 0, and we just copy down the divisor, right? And then again, it's a less than 0 remainder, so we do step 2b, add it back in there, and then, which will give us this here on that step, and then it restores this back to how it was before. And those carries take us all the way over into the overflow bit or whatever. And I should have said that I'm sorry, the quotient doesn't get moved here, it gets moved in step 2b, so there. Then step 3, we take that quotient and move it to the right 1 bit. Right? So now it's, you know, got 6 in there, right? So instead of the 12. All right. So let's copy these other values down. All right. This does get more interesting here in a second. All right. All right. So now again, we're going to do the subtraction for the fourth iteration. Really, the fifth total iteration. We started at 0, right? Depends on how you count it, I guess. So again, we're going to subtract this value out from here, all right? So basically subtract the 6 out from the 11. We're going to end up with 5 when we do this, right? So and bring this down and this down, right? So now we have this. We have a remainder that is greater than or equal to 0, right? Because all these above here, in this one, in this one, and this one, these were all less than 0. Hopefully I've been saying these are all less than 0. I apologize if it wasn't, but these were all less than 0 remainders. This is a greater than 0 remainder, right? Because it's positive. So in this case, we do the step 2a, all right? So now that step basically says we need to shift the quotient register to the left and set the leftmost bit to the right, to 1. So we're going to take that one here. We're going to shift this whole thing over and then set that to 1. All right. So, and then we don't do anything else. Step 3, we shift that divisor right 1 bit. Okay. So now it becomes 3. Right. So again, we subtract the 3 from the 5, and we'll end up with the 2 here. So okay. Again, it's a remainder that is greater than 0, so we do the step 2a. So we shift it over one place we shift the value over, and then set the least significant bit to a 1. So this gets all shifted over. Imagine there were more zeros out there. I apologize for the background noise. And then, so it's there, and then we shift that quotient over 1. And the quotient, the divisor over by 1 bit. Right? So it's now 1, right? And now if we were using the full size registers, we would do, is it the 33rd repetition? If it is, we would be done. All right, with 65. 33rd repetition, right? So yes, 65 repetitions or whatever that is. And then we'd be done effectively because here, anything, any number divided by 1, is a, right? That identity. So what do we have? So our quotient is 3, right? And our remainder is 2. Well, what's 11 divided by 3? Well, it goes into it 3 times. 3 times 3 is 9. 9 subtracted from 11 is 2, which is what we have here, right? So hopefully that simple example helps you out a little bit. If you don't believe me on the bit flips, just get the calculator app, right? In Windows or whatever, and see how it flips the bits. Right? Hopefully that helps.